Hello everyone, my name is Josh Weiner and welcome to Battery Interconnections. We're going to talk today about how you interconnect a battery system into the grid. There's several ways to do that, and we're going to figure out all the nuts and bolts and what's required to get a complete approved battery system connected to the grid that is compliant with prevailing utility rules. So I'm Josh Weiner. I'm CEO and founder of SEPI Solar. I'm with you today here with SEPI Academy, which is a training platform that brings sometimes nuanced and complex technical information and business and economic and financial information to viewers like you to help spread the wealth of knowledge of how to get these systems in place and mobilized and executed. We're going to talk about solar and solar plus storage as well as standalone storage and how these technologies and products come together to get interconnected in the grid. It is not all, some of it's straightforward, some of it's a bit nuanced, and some of it is cutting edge, brand new. That's literally coming out in November of 2018. Very recent stuff. So a little about me. I co-founded a company called Green Charge Networks in 2008, which ended up getting acquired by NG in 2015 and is on track to become one of the biggest battery integrators in the country or in the world. And in that process, I learned how to develop, install, and commission, interconnect, and maintain lithium battery systems over 5-10-year terms. So product development, business development, project development, and how these systems come together, all the quirks and idiosyncrasies you need to think about. And I'm going to share that here with you. So hopefully you don't have to go through all the same pain a lot of us early battery industry pioneers had to go through. So battery interconnections. First of all, the majority of you who have ever interconnected a battery, or in case you don't know, the most common way to interconnect a battery is actually quite simple. Battery electrons aren't allowed on the grid today, so all you do is file what's called a non-export utility interconnection, slap on a reverse power relay, protection relay on the system so that it basically turns the circuit off if you ever export power into the grid, and Bob's your uncle. You can get interconnected right away. And for most applications, that works out perfectly well. If you have a standalone battery system that you want to use to, say, do demand charge reduction or clip peak shave or clip demand for a facility, you don't need to export battery power into the grid. You rarely actually ever want to do that. I mean, batteries are net loads. They charge and they discharge. They're sort of like a load and a generator. But that process of charging and discharging is not 100% efficient. There's always some losses. So a battery is a net load. You wouldn't necessarily think to put electrons into the grid just to charge them right back. You're always going to charge more than you send out, and that's going to cost you something. So inevitably, the reason why we care about batteries, standalone batteries on the grid, is not to export electrons into the grid, but to reduce your demand from the grid, which means the electrons are never going out into the grid. They're just going into your facility. So that's why what are called non-export utility interconnections are really powerful for standalone storage. And the relays you use to do this are what's called a 32R or a reverse power relay. So basically, whenever the direction of power goes from one direction to the other, the relay sees it, detects it, and goes, oh, trip you off, and doesn't let you do that. And that's a UL-listed device that utilities know, love, and trust. So you slap that on your system, you file a non-export interconnection, and Bob's your uncle, you're going to be interconnected straight away. Where this becomes challenging is when we talk about solar. Because solar, of course, we want to export into the grid, while batteries, we don't. So we need different control systems for different parts of that solar plus storage system. And I'm going to go through that now today. So here's the golden rule of solar plus storage. Essentially, no battery shall... This is what the utilities care about. No battery shall charge from the grid, then discharge back into the grid at a later time and reap NEM credits. That is against the rules. That's a no-no. You're charging dirty electrons in your battery, you're sending the dirty electrons right back out and trying to get renewable credits for that. No way. It violates NEM policy. It violates all kinds of renewable portfolio standards and guidelines that all of us, industry and utilities and state, we all have to follow. So that's sort of the problem statement, or the it's really the problem statement is we cannot allow batteries to charge and then discharge and get NEM credits for it. Now here are two ways to prevent that. One is never ever allow the battery to charge from the grid in the first place, right? If it's never charging from the grid, then you know with certainty any electrons coming out of that battery certainly didn't come from the grid. And if the only thing that battery is connected to is a solar system, well, process of elimination. Didn't come from the grid, it must have come from the solar. So that's what we call the non-import method, where you basically don't allow any electrons into the battery unless they came from a renewable source, like solar. So that's non-import. And then non-export is the other way. The other way to prevent dirty grid electrons from being charged into a battery and discharged back into the grid is to never let the battery discharge into the grid in the first place. So, in a nutshell, if you want to ensure that a battery doesn't do that, doesn't violate the golden rule, never let it charge from the grid or never let it discharge into the grid. Non-import or non-export, or both. That's another option. On the part of several industry professionals, Seppi Solar included, my company, as well as Nextracker, as well as Avalon Battery Company and Ideal Power Converters, our companies got together and figured out a way to do a non-import utility interconnection that was compliant with this golden rule without adding a single bit of hardware or components whatsoever. And the beauty and elegance and magic of the system is in part due to DC coupling, which I'll talk about here in a minute. When you DC couple solar plus storage, you can make a slight and simple, easy firmware change to the inverter that, in a sense, mimics a non-import relay, but using pure only firmware. And that makes you compliant with this golden rule, which allows all kinds of magic to happen. For example, batteries under this paradigm, if you include this non-import firmware in a DC coupled system, you will be able to export battery energy into the grid and get NEM credits for it. This is completely unprecedented, has never happened in history. And it's just starting in November of 2018. These systems are actually going through utility interconnections in California and getting approved and getting installed right now today. This is happening. This is completely game-changing. And there's also some really awesome subtleties that allow you to supersize the solar system above and beyond what you could have ever done before. So this simple little firmware tweak solves a lot of problems. It gets much more solar onto the grid. It allows batteries to optimize the generation of that solar and exporting into the grid. And then it also limits the amount of power the utility actually ends up seeing from the system. So everybody wins. Customers get more solar, utilities see less power impact on their grid, and industry gets to sell more stuff in the meantime, because now we're changing our solar systems into solar plus storage systems, and that's easier to finance, often better margins and better returns from a business perspective. This is a win-win-win across the board for regulators, utilities, industry, like EPCs and developers and asset owners, and as well as for the customer, lowering their total energy usage and net costs. So how does this work? How does this non-import feature work? First, let's go to the whiteboard. We've got here, let's say, just for easy round numbers, let's say we've got a PV system right here. And let's say for round numbers, it's 30 kilowatts. Let's say we've got an inverter here. This is the lovely symbol for inverter. And let's say the grid is over here. I'm going to represent that with a meter. And these are all connected, and our lovely battery. And there's one additional thing I'm going to add here, which is some auxiliary loads. Because every battery has some amount of what are called auxiliary or hotel loads, which is just a fancy way of saying, you know, there's some controllers or maybe some HVAC or a fire suppression, a detection system, whatever, but there's some loads that you need available to the battery at all times to maintain the health and safety of the battery. And there we are. So now let's take a look at some of the ways that this pair, and by the way, sorry, one last thing. This is DC coupled because there's one inverter. When you have solar and batteries connecting together on the DC side of an inverter, we call that DC coupling. The alternative would be AC coupling, right? Where you have a solar system and a battery system, and they both connect into their own inverters before they connect together into the utility grid. This is what's called AC coupling. Twice as many inverters, more efficiency losses, more cost, of course. And from the utility's perspective, this will become more important later. The utility, when they rate the system, when they evaluate its size, if this is a 1 megawatt size inverter and this is a 1 megawatt size inverter, they will call the total system 2 megawatts. So this is a bigger system. And it's not exactly fair because, like I mentioned earlier, you're never going to really want to export this battery into the grid. You don't want to do that necessarily. But yet the utility will see 2 megawatts worth of inverters touching their grid, and they will say, you could, in theory, export 2 megawatts. There's nothing preventing you. So I'm going to call this a 2 megawatt system. And so that can be problematic if you're trying to stay under certain constraints. We'll come back to that. But this is a DC coupled system. So, and let's just put some round numbers here. I'm going to call this a 10 kilowatt battery, call it 30 kilowatt hours. And we're going to operate this battery at 500 to 700 volts. All right, there we go. And these loads are going to operate at something lower. They don't need 500 and 700 volts, maybe call it 24 volts. All right. So this is notice I haven't talked about battery chemistry, battery technology, solar chemistry, solar technology. This is as broad and as general as you can get. Any type of battery and solar system that are DC coupled and that have auxiliary loads fed from the DC bus or from the battery itself fit within this model. And actually, I don't think there's anything presupposing or limiting us from taking these auxiliary loads and feeding them directly from the grid. I think the model actually still works. Let's come back to that. So in other words, if this auxiliary load were fed from the grid, from a separate circuit, and not from the battery, this would still work. I'll come back to that. I'm going to claim that, and we are going to check to see if it's true. All right, so there we have it. Now let's look at all the scenarios. These are called modes of operation, right? All the different operating modes that this system could experience. So let's say the sun is up, or let's say the sun is rising, okay? Sunrise to sunset. This guy, colors. Solar is going to pump some energy out. Inverter is going to pump some energy out into the grid. We're going to get NEM credits for that. All hunky-dory, like any standard run-of-the-mill solar system, nothing revolutionary or game-changing here whatsoever. Very common. Now let's say the battery needs to charge. Well, solar energy comes into the inverter, some of it goes into the battery, and a little, whatever's left over, goes out into the grid. This came from solar. No harm done. This gets NEM credits. Battery gets the energy it's charging from. All great. Nothing out of the ordinary. Now, however, let's say the battery wants to discharge. Okay, so battery exports some energy. Well, this arrow is going to get a little bigger because now we have both solar and batteries. So the combination of the two now go out into the grid. Nothing wrong here. Battery was charged from solar a little earlier. It's putting solar right back out. Utility grid sees this energy coming out in the inverter. It's all solar. It's all good. Now, here's where we want to be careful. Let's say there's no solar or not enough solar. So there could be nothing or just a little itty-bitty arrow here. And now let's say the battery charges. Well, this little bitty arrow is much smaller than this big arrow. So where's the difference? Where's the energy going to come from? That guy. And this is what we have to prevent from ever happening. Because remember the golden rule, you cannot charge from the grid, just to discharge in the grid at a later time. And we're going to take a non-import approach to this problem. We want to prevent this scenario right here from ever happening. Whether the solar is on a little bit, early morning, late afternoon or something, or just cloudy, or even if it's at nighttime and off. This cannot be allowed to happen. So here's how we're going to fix it. This is how we're going to prevent it. The way non-import works is we are going to assume, or we are going to propose, that in the beginning of an average day, the solar is going to be generating a lot, which means most of it is going to be exporting. And let's say, again, since we want to show that we will never import from the grid, we're going to show this battery charging, and we're going to show how we're going to prevent it from charging from the grid. So this is the worst case scenario, right? We've got the battery charging, we've got some energy going out, but now it's sunset. The sun's going down. This arrow gets a little smaller, and a little smaller, and a little smaller, until eventually this guy flips. And now energy is coming from the grid. Before that even happens, just when it's about, this inverter, it is sensing these two ports right here. And it can see the difference between this guy and this guy. So long as this arrow is smaller than this arrow, everything's fine. But the moment this arrow gets too small, this is going to flip, and this is going to start charging from the grid. And there is some safety factor here. It's not when these are exactly the same size, but it's just when they're approaching the same size that the battery does something, the inverter does something really clever. It detects that this arrow is getting dangerously close to flipping because this arrow is dangerously close to the size of this arrow. And what does it do? It uses something called a voltage regulation mechanism. What it does is it knows that this battery operates across this voltage range, 500 to 700 volts. And what it does is just before these arrows line up and have the same magnitude and size, the inverter sets the voltage to something below the minimum operating voltage of the battery. Or in this case, since the minimum operating voltage of the battery is 500 volts, the battery sets it to 450 and says, hey, these arrows are getting close together. Now I'm controlling the voltage. I am the source of the voltage source. I am controlling this voltage at this port, at this bus. I am setting it to 450. This guy shuts off. It can't operate. It physically cannot charge or discharge from the grid. It's off. But guess what's still on? These auxiliary loads, right? Just because this is at 450 volts and the aux loads are at 24 volts, the aux loads can still take energy from the port on the inverter at 450 to feed its loads and keep the battery healthy and safe. That's totally doable. And now if you remember when I showed my dotted line, if these aux loads were being provided by a separate circuit, the same thing can happen. You know, there doesn't need to be this line, basically. As long as the inverter controls the voltage below the operating window of the battery, this guy shuts down, whether it has aux loads or not. So that's essentially what happens. And this guy always stays that direction and never charges. No importing into this battery. Now let's keep going. Let's say the sun starts to rise again. So now this arrow gets a little bigger. So now this arrow gets a little bigger. We're still off, right? Actually, that's not going. That could still be going, but this is off, 450. But now this arrow gets a little bigger, and the sun rises even more, and even more. And at some point, and again, there's some buffer here, there's some engineering safety factors, but when this arrow is a little bigger than the capacity of this arrow, basically the inverter says, you know what, we can turn the battery back on and there's plenty of energy here to prevent this from ever flipping around. So at some point it says, you know what, This 450 volt limit I just imposed on you, this voltage regulation, I'm eliminating it. You're back to your operating voltage. Everything's hunky-dory. And now the flow can proceed. The power flow can continue. This battery can charge. And of course, when it does, this arrow becomes a little shorter, but it's still net positive. It's still in a net export situation with the grid. And at no point did the battery ever charge from the grid. It charged from solar or nothing at all controlled by one inverter that can see everything. It can see the solar, it can see the grid, and it can see the battery and all the directional power flows between each port. This is relatively easy to do with a minor firmware adjustment in the inverter. And when you do that, when you make that adjustment in the inverter, one of the really critical things here is the regulatory process, because that change in the firmware of this inverter is something UL or a third-party testing laboratory or NRTL, NERDL, Nationally Recognized Testing Lab, can test for. They can actually put this in a laboratory, test that when solar is of different varying power levels, does it actually switch off this battery? Does it actually do its job? And that's something that can be tested for, slapped with a UL verification or certification logo or sticker or stamp, and a utility company can, in other words, the utility company can trust a third party to do that work for them. And that's really critical. You never want to be in a situation where it's you versus your regulator, with no check and balance in between. This is why UL is a great, this is why IEEE 1547 and UL 1741 for inverters was so popular and great, because it was something that could be verified in the lab. It did not need to be verified in the field on every single project. It's something you can test in the lab, put a logo on it, and utility companies, as long as it's got that sticker, I trust that it's doing its job the way it's intended, the way it was designed. And this is a UL verification process that is currently underway today. We've already had UL verify and witness test systems that do exactly this and put their logo on it. It's not a UL certification. There's no UL standard for this. It's a UL verification. It's a separate service that UL offers, and utilities are accepting it. It meets the intent of the golden rule that we just explained. And as long as you have a utility company, an underwriter's lab or an ETL or CSA or some third-party NERDL testing it, it's completely valid and compliant. So that's really exciting. So now you might ask, what are these tests that UL is currently doing? Well, one of the tests is they want to make sure that when this inverter switches from export to import, when it rotates or flips between the two, that just before it does that, basically, that it'll be able to sense that that is happening. It'll be able to sense that this arrow is getting smaller and smaller and smaller and is about to flip. So basically, they put this inverter on a bench or in the field, and they witness test as the solar is coming down, can it actually see and measure and monitor and report on the power flow on this side of the inverter? Pretty simple. Then it also tests to make sure when it sees that, can it make a command over on this side of the inverter to reduce the voltage, but to some minimum threshold or some set point that is hard-coded and programmed into the inverter? Can it do that? Pretty simple test. So it tests the inverter can see this, and that when it does, it switches here. And that's it. That's all the testing that is done on this inverter. The other test that's done is on the battery side. Does this battery connected to this inverter, what is its operating voltage window? And does the battery actually turn off when you venture outside of that operating window? So they take the battery, put it on a bench or in the field, and they witness test what happens when you force the battery voltage, or the voltage set point here on the bus. What happens when you change that bus voltage to 400 or 450 or 100 or anything below 500? What happens? Does the battery turn off? Yes or no? Pass or fail? So that's a pretty simple test. You say it's 500, 700 volts. Let's double check that. Easy, done. In fact, I think in the future this test might go away with UL 1973 or 9540, which test a variety of specs on the battery already, like current and capacity and voltage and fire safety and enclosure and NEMA ratings. I think this might actually already get covered in another existing UL standard so that this test that I'm describing doesn't need to happen twice. So in the future, it's pretty probable that only the inverter will need to be tested, not the battery and inverter together. And that'll streamline even more. It'll allow you to mix and match different batteries with different inverters on different systems in real time, and you don't need to go into UL and do all that testing all over again. And then finally, the last thing that you want to test in all this is what happens when you swing the power up and down on the solar side very rapidly or frequently, because we all know solar is not necessarily always a smooth ramp up and ramp down type of curve, sunrise, sunset. Sometimes there's clouds and weird weather, and you can see the solar turn on and turn off and go from full power to no power in seconds. And so basically it's like a stress test. All these tests I just described all need to be able to work even when the solar is fluctuating up and down very rapidly. So that's the last test that we do, or that UL would do, to see if the solar plus storage system complies with these NEM requirements. Here are some examples of this test actually being performed. What you see on the screen in front of you is a battery at a certain voltage in the dark line labeled DC voltage. So on the far left, you see a constant battery voltage. This is the voltage that the battery operates at. The yellow or gold line is the PV power, so the sun is up and the power is up, and that's why you see the yellow line or the gold line up high. The sun is up, the power's flowing. And then of course you see the battery is charging, the green line, which it can do because it's operating at its voltage window. And the red line is the utility power. That's what we're actually exporting into the grid. That's going out into the grid. So it makes sense that the red line is below the yellow line, right? Because the yellow line is all the total energy coming out of the solar system. The battery is charging green, so some of it's going into the battery, and whatever's left over is going out into the grid. So big arrow up on top, smaller arrow in the middle, and the tiniest arrow going out into the grid, just like we were showing on the whiteboard a moment ago. But now, notice what happens when the yellow line, so now the sun is setting, because you see this yellow curve is slowly coming down. The sun is setting, solar power is coming down. And at some point, the red line gets dangerously close to zero. So you see how the red line begins at a positive level, and then as the solar starts to ramp down, so does the red line. Because the battery is just constantly charging. It has a constant draw off the solar. So if the solar is coming down, it's the grid export that comes down with it until it gets dangerously close to zero, and it hits a minimum threshold, at which point the inverter says, uh-oh, you're about to import energy from the grid because your battery is charging and your export out into the grid is going down. So you're about to import energy from the grid. You're getting dangerously close to zero. I'm switching you off. And at the same time, as you get dangerously close to zero, as the red line gets close to zero, now the battery voltage turns off, or it gets set below the operating window. So it was about 500 volts before, now it's dropped down to something less than that. And what does that do? When you drop the voltage down on the battery, the red line skyrockets back up. It spikes because there's no battery charging. The battery's not taking any energy away from the solar curve. So the battery is now off. So all that solar power is now going out into the grid. So the battery is off now because the voltage has been set below. All the solar is now going out into the grid, and the difference now between the yellow line and the red line is just inverter efficiency, basically, and system efficiency. So that's why the red line and the yellow line are slightly off from each other. One is DC and the other is AC, so to speak. So now what happens is the battery is going through a clearing time. The inverter is watching to ensure that there is enough going out into the grid so that we're not getting, again, dangerously close to zero. And it sees that. The red line came back up. There's a lot going out into the grid. And we get through a clearing window, a clearing time. And the inverter says, you know, the red line is not dangerously close to zero at all. It's exporting power. Hey, battery, you can turn back on if you want. So the voltage, after a few moments, actually turns back on. The voltage jumps up. That's why you see kind of this valley and then a peak on the voltage line, because the inverter actually sees the red line is far above zero and turns the battery back on. It says, hey, you're okay to turn back on. So it turns the battery on. And after waiting for another period in time, the battery just kind of waits. It lets, checks to see everything's up to snuff and into spec. And so it sits there, and after a certain amount of its time, it says, okay, I'm ready to charge. You gave me my voltage back. The red line's above the zero, and I'm going to go ahead and charge again if I need to. And so it does, and you see that green spike of the battery trying to charge. Well, guess what? It tries to charge, it ramps up, but the red line dips way down low. Because obviously if the solar is only so much, if we only have so much supply from the solar, and the battery tries to gobble up a lot of it, the red line's going to drop close to zero, and once again, we're in danger of importing from the grid, which is not allowed. And the inverter sees that, and it repeats the whole process all over again. So the PCS or the inverter sees, oh, the battery's trying to charge, it's dropping my red line way too close to zero, I don't like that, we don't allow that, it violates the golden rule, so guess what, I'm turning your voltage off again. And so the voltage drops once again for the second time to a threshold that the battery cannot operate at. And as a result, the battery turns off, which is why the green spike comes right back down, and why the red line jumps right back up. And again, it goes through another clearing time and the whole process repeats. Now, this is a worst case scenario. An engineering or a product manufacturer should never design a system that allows this hysteresis or this repeating motion to go on and on and on. Really, what would happen in nominal, normal operations is the battery would never turn on and charge at this level to begin with. It knows the rules. It doesn't need the inverter to tell it. We're all monitoring with the same data on the same system. So effectively, this doesn't happen in real life. This is a demonstration to show that even under worst case scenarios, the inverter will never allow the battery to violate these rules, these NEM compliance rules. And this gives utility companies and regulators great assurances that the system will do what we say it's going to do, even when it's not operating correctly, even when the battery tries to charge too much when it shouldn't. Because the inverter is acting as like the last line of defense. It's the safety mechanism. And now this entire procedure can be repeated in the other direction, like this graph shows, where the solar starts off really low, because say it's nighttime, and starts to ramp up. And as it ramps up, the battery can turn on, and the inverter can shut it down. It's like, there's sort of this dance between the battery and the inverter that goes on and on when we're ramping down or ramping up. And then we can do this much more quickly. We're showing a slow ramp of the solar up and a slow ramp of the solar down. But there can also be very dramatic and fast ramps up and down. And so we test for that. And you see in these subsequent graphs exactly that. And then you can see it the other way too. You can see what happens if we keep the solar constant and we ramp the battery charging instead. So whereas before we were holding the battery charge constant and ramping up and down the solar faster and slower, now we're keeping the solar constant and ramping the battery charge up and down faster and slower. And you see the exact same behavior over again. There's absolutely no difference. This is identical behavior day in and day out. We're just twisting and pulling different dials, knobs, and strings to see the same behavior. So that's test number one. Test number two shows what the battery does when the voltage is set differently. So test one shows how the inverter works under different operating conditions. Test number two shows what the battery does under different operating conditions. So what we're seeing here is the green line is the voltage that is being set by the inverter, and the darker line is the battery power. So you see where the green line, if you start from left to right, you'll see where the green line suddenly drops. And it drops rather quickly, and the battery responds just a moment later. As soon as the green line gets set down, the battery responds immediately. And pretty quickly the battery drops its power rating. So that's what we want to see from the battery. We want to see that the battery responds to changes in voltage. And what you'll notice too, you might ask, why doesn't the battery power go to 0? Isn't that what it's supposed to do? Right, you would think so, but these are auxiliary loads. Remember those auxiliary loads? That's where that 500 watts on this graph is going. So the battery has been shut off. You can see that in the dramatic spike in the jump. When the green line comes down, the dark line does too. That's the battery turning off. But we still see some residual load coming into the battery because that's the auxiliary. And you see it fluctuates too. Pumps, or if there's HVAC and pumps and motors and controls and fire suppression, they might turn on and off at different times for different reasons. And then you see when the battery voltage, when the voltage set point jumps back up, set by the inverter, the battery, it sits at its lower voltage for a period of time and then turns back on after a certain amount of clearing time has gone by and it knows it's safe to export power again or to start powering up. And that's why it jumps right back up toward the right side of the graph. And we can repeat this for different speeds of voltage ramp rates. You can ramp the voltage down slow, you can ramp it up fast, and do anything in between. And so you just see different volt ramp rates, and we want to check whether the volt set point comes down quick or slow, the battery responds to it. And that's what test 2 does. This next test, we want to just check that the firmware can be recorded by the manufacturer, by the inverter manufacturer. So, if an inverter manufacturer makes this non-import functionality into the firmware of their inverter, we want to be able to check the version of that firmware, that number, that version number, and be able to cross-correlate it with the manufacturer's part number or the SKU number. And we just want to make sure that model of that inverter has this version of that firmware, and if so, the inverter does what we think it's going to do. Pretty simple. It's basically just checking a specification. And this specification, of course, can be checked by UL and stamped appropriately or approved. And then another test that we do actually is test number 4, what we call test number 4. This is actually where we test to make sure that even if there's an EMS, an energy management system, even if there's another brain or a controller on the system, that it will always be overridden by the firmware in the inverter. This is actually one of the reasons why we call it firmware, not software. Firmware, like the name suggests, it's firm. It's built or hard-coded, if you will, into the inverter and is unadjustable. You cannot get in there and tweak it and change the rules. Utilities and regulators typically don't like it like that. So this gives assurance that even if there's another brain or another piece of software in the system somewhere, like in an EMS, whatever it does, the firmware is going to take control. And so even though EMS and firmware, or software and firmware, are both types of software, one is inherently, you could define the difference as one is inherently not unadjustable or non-adjustable. So we test this. We test that if the EMS commands the battery to export power, even though it's only operating at 450 volts, that it can't. Or if the battery is at its operating voltage window, that even if we're dangerously close to 0, that red line, if we're exporting power out into the grid, but just only a little bit, not very much, that if the EMS commands the battery to suddenly charge a whole lot from the grid and drive that red line under 0 and start importing grid electrons into the battery, that even if the EMS were trying to do that, the inverter will take over and say, nope, this firmware in my inverter does not let you do that. This is a hard-coded feature, a hard-coded function. Nobody can tell me otherwise. That's test number 4, and that's very easy to check. Finally, test number 5, the last one is the one I mentioned earlier, how PV can be very intermittent. It can turn off, it can turn on, it can ramp slow, ramp fast. So, this is sort of like a stress test. We just want to see if we can break this, the functionality of the non-import firmware that we've been talking about. So, this is like a little kid with a bunch of dials in an operating center, like turn everything on high, turn everything on low, turn the battery on high and the solar on low, and the solar on high and the battery on low, and vice versa, and just see if we can break this thing. So just to wrap this up, the beauty of this, the reason why this is really, it seems simple, right? All we're doing is turning an inverter into basically a non-import relay. We're just not allowing one port of the inverter to ever import energy from another port of the inverter. The reason why this is so powerful is for the first time in our industry's history, A battery can, if and only if it's only charging from a renewable source, it is allowed to export those electrons into the grid, and no measurement and verification is required. When you have an AC coupled system, you actually have to measure both the solar output and the battery output to make sure that the battery is actually importing electrons from the solar. If you wanted to impose these rules, if you wanted to make a battery that is AC coupled NEM compliant, but it's AC coupled, you have to count every electron that goes into the battery also necessarily at the same time came out of the solar system. And you build time series graphs of the export from the solar and the import to the battery and make sure that the battery is never charging more than the solar can possibly output, right? Because if the battery is importing 100 watts, but the solar is only exporting 1, you know the other 99 watts, or the remainder came from the utility company. So in AC coupled systems, you need to do what's called M&V, measurement and verification. You have to count every electron, you audit them, you report them, you get into a negotiation with the utility that you never violated NEM, you get into a negotiation with the IRS that you never violated ITC, because by the way, these NEM rules are exactly the same rules for ITC. So you're going to be discussing both with the IRS and the utility company which electrons went into your battery. And that's measurement and verification on AC coupled systems. With DC coupled systems, guess what? Every electron that goes into the battery necessarily came from the solar by design, as tested and verified by UL. So absolutely no measurement and verification. This thing works by design. You don't have to check it. You don't have to measure it. It's done. That's pretty incredible. And that's unheard of right now. Again, the controls are hard-coded in the system's firmware, so there's absolutely no way to break this. This is hard-coded in, verified by UL, never going to change. Good for 20 plus years. This doesn't rely on communications whatsoever. Utilities and manufacturers, we worry about communications. What if communications drop? So if communications are vital to the health and safety or compliance of an operating system, then you better make sure those communications are really robust and you better test and verify and UL list all those communications. Well, not in this case. This is simply done with power control or voltage control, period. No communications. Also, because it's DC coupled, all of this can be hard-coded and built into the inverter, which is very simple to do. This is a software change, or rather a firmware change in the inverter. Relatively simple. You notice it was technology agnostic. We didn't define any particular type of battery chemistry or inverter type or IGBT or anything. This works for any DC coupled solar plus storage system. It's repeatable because you can do this with any number of inverters. And as I mentioned earlier, once UL accepts the ratings of the battery from UL 1973 or 9540, some of the tests we just went through won't even need to be done. They will have already been done, and UL can just check their own UL-listed spec sheet that they tested and listed with the battery from an earlier 1973 test, for example. All of this was designed to comply with NEM policy, which is really important. This is how we allow batteries to export into the grid and reap NEM credits for it, actually get paid for it. I mean, that's really incredible. Basically, it could be in the middle of the night, at midnight, and the utility will suddenly see an export from our DC coupled solar plus storage system and allocate NEM credits in the middle of the night. That's never been done before. And if that's the right time to discharge the battery based on tariff rates or whatever rate pricing structure system we're in, we're literally making the sun shine at night. And we're doing it in a perfectly NEM compliant fashion. So we just talked about how this DC coupled system makes NEM more robust. And guess what? It also makes the ITC more robust. Because in order to get the 30% ITC for batteries, the exact same rules apply. The rule is, in order to get 30% ITC for the batteries, 100%, not 99, not 95, not 85, 100% of the energy going into the battery must have originated from a renewable source. And you can bet that if the IRS sees a utility interconnection agreement from a big bad public utility certifying or authorizing the system precisely because it complies with NEM, which means it never ever charges from the grid, you can bet that you have two bloated bureaucracies now agreeing with each other and on your side. You've got the IRS saying, wow, the utility company approved you precisely because you don't charge from the grid. you've got to be ITC compliant because those are the same rules that apply to IRS. So that actually reduces ITC risk out of the project, having a DC-coupled NEM compliant system. Now the ITC is rock solid. And that's not even the best part. Here's the best part. There's a cap on NEM systems. Some consider it a hard cap, some consider it a soft cap. At least this is true in California. Not all states abide by this. But in California in particular, under NEM 1.0, which was the first stage of evolution of NEM, when there wasn't any solar on the grid, NEM 1.0 set the rules and we all played by them and it was all great until we hit a certain saturation threshold on the grid, at which point we had to transition out of NEM 1.0 and come up with new rules. Because as you put more solar on the grid, the rules do need to change. The grid gets more difficult and challenging to manage. Power is flowing in multiple directions. This is something that the utility companies have to deal with. So it's only fair that we reevaluate as saturation of renewables on the grid goes up. Do the rules still make sense? Do we need to change them? And in NEM 2.0, they certainly did change. We decided that under NEM 2.0, we should be allowed to actually go over a megawatt. On NEM 1.0, it was a hard stop at 1 megawatt. If you wanted to go above a megawatt, you weren't necessarily under the NEM program. You were in a custom negotiation with the utility for rates and payments. But under NEM 2.0, they actually lifted that cap with a nice little string attached, which is if you go over a megawatt, you're NEM eligible, but now you are responsible for 100% of the upgrade costs that larger solar system might require on the grid, because not all the feeders and reclosers and substations on the grid can handle that kind of power, that amount of power. And this hints at what the utilities care about. Utilities don't like to manage more power than they need to. So how does this impact us? Why is this important? Well, in a DC-coupled system, this could be 1 megawatt, but the solar could be 5 megawatts, and the battery could be 4, right? Why not? You could have 5 megawatts coming out of this guy, 4 of it could be redirected into the battery, while 1 ends up going out of this inverter over to the grid. The utilities companies' interconnection departments will rate this system as a 1 megawatt NEM system, even though you're giving the customer 5 megawatts of solar. This does all kinds of amazing, cool things. You're giving less power to the utility, which is what they want. You're giving more energy to the customer, which is what they want to offset their utility bill. And you, the business innovator, developer, EPC, gets to sell more stuff. You get to sell a battery along with all this stuff. And that makes the projects easier to finance, because financiers like bigger projects with more money at stake. That amortizes legal costs and all kinds of things and allows to move more money into cash flow positive places that investors and ITC owners all like and debt investors like. So this is good for the utility company, it's good for the customer, and it's good for industry. Win, win, win across the board. This literally is like a loophole that allows us to get even more solar on the grid than ever before. So unlike an AC coupled system where you would have a solar panel, let's say you had 5 megawatts of solar and a 4 megawatt battery, and they both went through their own inverter. Well, this inverter obviously needs to be 5 megawatts to allow the full 5 of the solar through. And this certainly needs to be a 4 megawatt inverter to allow all the battery energy in and out. And then if these guys connect together on the AC side at the utility, well, the interconnection department says, this is a 5 megawatt system, this is a 4 megawatt system. You could potentially export up to 9 megawatts into my grid. And that's a lot of power I got to manage. I got to make sure the feeders are big enough, the reclosers are big enough, and the substation 5 miles down the road is big enough. And oh, by the way, you're responsible for all those interconnection costs and upgrade. So AC coupled is actually really challenging to interconnect from that perspective. So it's all about DC coupling for now. And it's all about supersizing the solar to help the customer, limiting the power to the utility company with a single inverter system and a bigger battery to make it all happen. This effectively stacks 3 revenue streams. You hear in energy storage about stacking revenue. Well, here they are. One is more PV than before. You defer infrastructure, because now you don't need to pay what could have been under this regime, the AC coupled regime. You might have had to pay $1 million or $2 just in system upgrades. Not in this model. You defer all that cost. This essentially makes the project a slam dunk. People focus on, cost of energy with the PV. They also focus, because you get with this demand charge savings. I'll tell you though, having modeled many of these, I can tell you this is just what makes this thing a slam dunk. These are pennies compared to this guy. You can get so much energy for the customer and defer so much of this. I'll take the Pepsi challenge. Send us some models, send us some customers with interval data. We will model it together and we will show you the incredible amount of revenue that comes from this model. This is really, truly game-changing. And then if you use something like a flow battery that can handle big, deep discharges every single day and manage the solar, because that's in this kind of a model with a battery that's dynamically working with the solar every single day to maintain this 1 megawatt compliant kind of stuff, you really need a battery that can handle deep discharges every single day over and over again for many years. I mean, you want these two to be linked. So they're pretty much an integrated system. So flow batteries tend to work really well in this application. And what's great about that is you can get some time of use arbitrage, because it doesn't cost anything to charge the battery. With a battery like a flow battery that doesn't degrade per cycle, it doesn't care about cycles because the electrochemical reaction is purely aqueous. This thing, there's no cost to cycle it more and more. So once you've done all of your demand charge for the day, you've shifted all the solar you need to comply with NEM compliance and also defer all the infrastructure costs. Whatever's left in your battery, spit it out at a high energy rate toward the end of the day, like late evening, and recoup. And this can add up to like another 5 or potentially 10% revenue of your top line revenue. Whereas this might be more like 15 to 25%. This could be like another 25%. And this is just like the infrastructure. I mean, this kills projects on a regular basis. At Seppi Solar, the design engineering firm that I'm CEO of and founded, we see projects die a lot because you don't know what these costs are until the deal has been modeled, proposed, bought, signed, and you've submitted utility interconnection paperwork, and then you find out, oh, hello, by the way, you need to pay an extra $1 million or $2 in upgrade costs in order for us to interconnect you. That's even happening with systems less than a megawatt, because parts of the grid are now starting to get so saturated that we can't even get up to a megawatt. We can only get up to 900, 800, 750 kW. So batteries come in to save the day all over the place. We throw in a battery. Not only do we get rid of the infrastructure costs, but we get some more revenue from demand charges and a little bit of arbitrage on time of use rates. Now the project actually pencils better than it did before, eliminates even more risk, and everybody's happy. So if you're stuck in that kind of a case, give us a call or reach out, because we'll definitely help with that. Otherwise, you can do the conservative route and go through all the utility interconnection process before you sign a deal with a customer, and go through that pain a priori or up front. That's another way to do it. And then you find out all these costs downstream and figure out what to do with it then, if you want to proceed with the project or maybe factor in storage and get a better return on investment for your customer. So that's it. That's battery NEM compliance. Super exciting stuff. This is game changing. We're going to get more solar onto the grid. We're going to get we're going to get more solar for customers, less power onto the grid, and more batteries to do really cool things, which after we've accrued the ITC and maybe when the policies evolve over the next few years, we can start changing some of the certifications of these guys and start using this battery in new ways for, say, demand response or distributed energy resource management, and with FERC and the wholesale side of the utility grid. All kinds of cool things are coming down the pike where these large batteries that are now all over the place can actually do a lot of other things aside from this really cool model for the customer. I mean, how would you like it if the utility called you down the road and said, hey, I really need 4 megawatts of power right where you're located tomorrow at 3 p.m. and I'm willing to pay you to do so. Would you mind doing that for us? Yeah, absolutely. I need to temporarily export a little more power out of my inverter. Is that cool? Yes, great. So anyway, we see these models starting to happen. Super exciting. Thanks for joining us. Batteries can export into the grid, reap NEM credits. Customers get all the energy they need. Utilities are happy. Asset owners are happy. Will recoup their investment. And we're going to get some really sophisticated, well-integrated, and easy systems to install out into the field that make the world a better place for everybody. Thanks for joining us.